Okay. Okay. Um, so last time, I briefly mentioned the basic idea of Dubushin's estimate. So today, I will just give the full details of the Dubushin estimate. And from Dubushin estimate, we can directly get mean field limit on the assumption the interaction kernels is Lipschitz and skew symmetric. Basically, the essential assumption are Lipschitz. Okay. So if you have questions, you can stop me at any time. Okay. Let's just briefly recall the notations. So first we have the ODEs for n particles return in the phase space. So we have n particles. So Zi, Zj. Since we already made all the assumptions, so K is skew symmetric. So here we just write in this way. So I equals to 1, 2, 2n. So here, so we assume K is skew symmetric. And globally Lipschitz. And Lipschitz. Okay. So actually, on the other hand, so our goal is to compare ODE system with mean field PDE. So last time I didn't write this, I didn't talk about intuitive idea. Why do you get the mean field PDE in this way? So here actually is F. So kappa F equals to 0. So of course they are all associated with initial condition. So here kappa F, which depends on time and also position Z. This is an integral operator, which is defined like this: K Z prime F T dz prime. So here F is a probability mirror, and we integrate with respect to Z prime. Okay. So our goal, right, as in all these courses, is to show the convergence of the empirical mirror or other quantities, maybe with the same rule as empirical mirror, will converge to F. So here, if you just want to show the convergence of empirical mirror, so which depends on time t, so this will converge to the solution Ft. But of course, right, so if this is our goal, you can just think this as mean field limit. So of course, to realize this, we need the initial assumption. Initially, so Fn 0 we need the reconvergence from the initial empirical measure to F0 dz. right? So this is the initial condition. So this is initial condition. These are initial condition for the ODE system. These are initial condition for PDE, mean field PDE. And from the right-hand side, so we evolve. So from the right-hand side, we evolve ODEs, or particle system. From the from the left-hand side, we evolve ODEs. Right? We run the dynamics of ODEs. From the right-hand side, we evolve PDEs. So basically, all we want to do, right? So in this topic, is to establish this diagram, right? So the first line, the bottom line is initial condition, and we want to show, right, under the initial convergence, and we want to show this convergence from empirical measure towards the solution or PDEs will hold, like for certain t. For instance, for some period of time. Okay. So since we already made a very strong assumption for K, this is not a very hard task. So which is done by Dubushen and several other people in 70s, last century. So so I will just do that in detail in this lecture. But before we do that, let's just briefly mention, right, why this is possible. Okay, so I mean, what is the intuitive idea why this is possible? So first, you can think the following. So basically, mean field limit is the essential part is like law of large number. You can think in this way, or in the Lipschitz case, is basically just the stability of mean field PD. We can think in the following way. So let's assume we have n particle. We have n particle, z1, z2 to zn. So each particle zj is a random variable. So let's assume this random variable and time t satisfy a law, probability density function. So what is this quantity? Okay, let's fix zi. So if we fix zi here, right? So this is just a sum of n quantity, right? So this is the area. Sorry, let me close the door. So this is just a sum of n random variable, right? Zi is fixed. You can think this as conditional things. Or so this is just a sum of n random variable. If we fix Zi, okay, and by law of large number, so we expect this convert to something. So here is some conditional expectation. Kzi zj. So if we write this explicitly, right? So it's something like it's just the integral. Let's fix zi, and here is z prime f t z prime. So if n is very large, right? So this this tells us the right-hand side in the ODEs can be represented by the same form, right? Like this. So this integral we write as, so we just write as kappa f tzI. So this hints us the original ODE is just n copies of the following equation, zi. So the dot, the time derivative of z, so equals to kappa f tz. So original ODE system can be approximated by this. What's this, right? So this is nothing. This is called mean field characteristics. So what mean field characteristics actually is exactly the characteristic equation of mean field PD. I just let me just write in a shorthand notation. So mean field dynamics. So let's just write everything. So this is mean field dynamics. Okay. You can check this very easily. So actually, this is a general things, right? It holds for all the equation in the following form. It's called continuity equation. So usually, right? So let's consider a continuity equation like a partial T rho plus divergence Z rho U equals to 0. And we associate this continuity equation initial data. Let's just call this initial Z, right? So this is a probability density in RD, right? So rho is a density function Z, okay? And U equals to UTZ is a velocity field. This is RD value, okay? So here we ignore all the regularity assumption. We assume everything is as nice as possible. So here, if we write the characteristic equation, so what's the characteristic equation? So it's just Z dot equals to U T Z. So we give certain initial data, let's say Z0 equals to Z initial. So this ODE is the characteristic equation of this continuity equation. So we can solve this, let's say if U is explicitly known, we can solve this ODE explicitly, but sometimes like in the mean field dynamics, so U actually depends on the law of Z itself. So probably we cannot solve that explicitly just by the ODE itself. But let's assume we can solve this flow. So we can solve that. Let's say we starting from initial, so in, let's say, so we can get a flow, let's say Z and time T, starting from initial data, let's say Z initial, okay. So this rho T actually is the push forward. So is the push forward mirror of the initial mirror. So this is very easy to check, and you can read Gauss notes for details. But I just want to mention this. Okay. So last time we already mentioned. So for the ODE system above, we just written. So the empirical measure. So this is let's just recall. So the empirical measure F T dz. So which is the push forward. So this is the empirical measure and time n. So Zn initial is the initial data. So ZIT. So the empirical measure so is a weak solution. Of the mean field dynamics, the mean field PDE. So given, so the mean field dynamics above. So this can be checked. This can be checked very easily. I will just skip that. You can find all the proof and list a sketch of proof in Gauss notes. So I just skip this. Okay. So there's a one page the sketch of the proof. You can check, but I will skip all of that. Okay. Okay. So let's use one uniform. So as I said, so the ODE system can be returned, right? If you just use the empirical measure, you just use the empirical measure. So we can use the mean field PDE to represent both the limit PDE and also the ODE system. This can be represented in another way. Okay, so let's just write that. So this is theory 2. And we will need the notation here, right, to do the distribution estimate. Okay. So under all assumptions on K, so skew symmetric and global Lipschitz, and for each we choose initial data psi n. This is psi n in RD, and each Fourier probability measure so mu initial, which is in P1 RD. So P1 RD is just the probability measures the set of probability measures with finite one moment. Of order 1. So for initial that initial position and initial measure, so there exists a unique solution. So denoted by the following. So this is just the characteristic flow starting from initial data psi I, psi initial and initial measure. So this is of C1 class, is differentiable with time, which solve the mean field characteristic equation. So let's write in the following way. So kappa is the integral operator we just defined above. mu initial, and the initial data is just cosine initial. Okay. And we call this mean field. So we call this mean field characteristics. And the MEMP is called the mean field characteristic flow. So this MEMP, the MEMP, so this MEMP is called mean field characteristic flow. Mean field characteristic flow. Okay, so so of course, right? So this can be right. So since this is already right, if you just choose mu initial, right here, the mu initial as the f initial, right? As the f initial here, for this equation, right? So we can just follow the characteristics and give you the solution of the mean field PD. And also, right, this can be checked directly by the uniqueness part of this theory. So if we start him, from empirical measure, so let's say if we're starting from initial empirical measure, so this is the initial data. So TTZN initial is just the solution of the ODEs. So these are ODEs. Okay. So then ZI, so ZIT is nothing but just this. We just plug the initial data, ZI initial, and we apply the initial measure as the initial empirical measure. So we can solve the ODEs via the mean field characteristic equation or the mean field characteristic flow. Okay, this can be checked very easily. And the proof of this theory, so is exactly, so this is just a mirror version. So this is just how to say that? This is just a Cauchy-Lipschitz theory again, but with initial mirrors or something. So you can run the like Picard iteration just in the classical theory of Cauchy-Lipschitz in the well positions of ODEs. But here, right, we have the initial mirror. So the mirror is the dynamics, right, is self-consistent. The mirror plays a role here, and the flow will push forward the mirror. Right, there's an evolution of mirror, and the evolution of mirror is given by the mean field dynamics, and the flow, right, the flow is given by the self-consistent ODEs. Just this dynamics. Just this dynamics. Okay. So I will skip the proof. You can find the proof in the notes. But I want to emphasize the following. So this mean field dynamics can be retained. So in so this mean field dynamics can be retained in a nice way. So by rewriting this, by rewriting the integral operator. So I will just copy below. So okay. So mean field. So mean field characteristic equation. So can be written like in the following way. So partial Tz T cosine initial mu initial, so equals to the integral. So Zt cosine initial, so mu initial. So here is Z prime and mu T dz prime. Oh, this is the equation, the first equation. I just rewrite the integral operator here as we just explained that. Okay, but we can using the second equation, right? So mu t is the push forward measure under the flow itself, right? So we can using channel measure formula. So we can rewrite this as z t cosine initial, so mu initial. So here we change z prime. So z prime actually equals to the z prime. Let's change using a map. Z t. Sorry. So here mu t. So is the push forward map. So z t mu initial. So this is a characteristic flow, and if we take the push forward mirror of the initial one, so we get mu t, right? So we using the change of mirror formula. So what's that, right? So it's just a k, sorry. So then we get z t cosine prime mu initial. So d, so mu initial d cosine prime. So this is a new formula. So if we write it in this way, right? The mean field dynamics, the mean field characteristic equation can be written in the following way. And the integral now does not involve the measure and time t. It only involves the measure and initial, right, and time 0. And we will need this. We will need this. Okay. So of course, right, since this is trivial, 0, right, it's just a way we write that. Okay. Okay. So now we have everything ready, right, to give the Dubruchin's estimate. As I said, right, so Dubruchin's estimate is just a Grunwald type estimate. You have seen that in a lot of places, for instance, in establishing the Wilposians of ODEs. So actually, this estimate is just the following commutation. I want to show you first. So it's a very basic calculation. You probably see that like in like when you are undergraduate students. But I still want to show this calculation because this is the essence of almost in a lot of works in mean field limit. If there are regularity, like let's say the K, the kernel is Lipschitz or something like that. So let me just show you this commutation. Okay, but I will we will use this. We will use this. Okay, let's just do the following computation. Okay. Let's consider, or let's just I kind of change the notation a little bit. So let's just using the same dynamics, but I kind of using different notation. But since we will compare two trajectories, it doesn't really matter. Okay. So here, this is the same equation, but I just change xi to zi. So I equals to 1 to n. So let's say we have two trajectories. So the first trajectory is just x, x1 to xn. And the second trajectory, let's put t here. Let's put t here. But for simplicity, I will just ignore all the t when I doing the computation. So this is y1t, ynt. So these are in RD n dimension. And let's assume k is Lipschitz, right? K is Lipschitz. And also kz prime is minus kz prime z, right? So we assume k is as good as we assume. Okay, so now I want to compare these two trajectories. So compare, I want to compare these two trajectories. Okay, so it's very easy to do that, right? Just take the derivative. Let's say we just take the derivative, but we need a norm, right? To compare two vectors, we need a norm, right? Let's just using this norm, P norm. So P is bigger than 1 or equal to 1. So U is just U1 to U capital N. So which is norm, normalized norm 1 over P. Okay. So now we take the derivative of xt. Let's just using x and y. Okay. So actually we can put absolute value like here, but we only care about the upper bound. So so I will just do like this. So this is controlled by the derivative inside. We can put the time derivative inside the norm. Yeah, it's very easy to check. So using the equation, we can have the following: 2n. So here is k x1 xj minus k y1 yj. So here something like that, right? Is the first coordinate, then the last coordinate. So here is xn xj minus k yn yj. Okay, so it's just a trivial computation, and we're using the triangle inequality. We can put this sum out, and we can use the Lipschitz property as well. So I will be a little bit quick, but you can check that by yourself using the Lipschitz property. So I put the Lipschitz constant as gradient k, both in the first variable and the second. So you can check this. You can check this. So then this is less than gradient k infinity norm x minus y. p norm plus x minus y 1 norm. So this 1 norm comes from, right, so there's a common term here, the common terms here, and then you sum with respect to j, so you actually get 1 norm. But we know 1 norm is controlled by p norm, so here is just a 2. Okay, so what we have, right? So we have this time derivative of the p norm of the distance between a trajectory x and a trajectory y. So here by Grunwald, right? By Grunwald inequality, we can conclude directly. So this is controlled by the initial distance, and there's a factor. There's a factor here. Actually, this is what we expect in Dubushin's estimate as well. Dubushin estimate essentially is just this computation, but we kind of do in a different way, because here we just compare two trajectories. But if you think this carefully, right, if you're using a lot of particles, right, in very high dimension, and you let the n to be the same, right? So right, you're using, let's say one is a measure of mu1, another is a measure of mu2. We can approximate this mu1, mu2, right, by a lot of particles, right? So the only thing matters here actually is just their initial difference between the positions, right? So that's the same idea. Actually, it is almost essentially the same for what we will do, right, for Dubushin estimate. Okay, yeah. So this is the basic computation, which shows, right, if k is nice, right, the two trajectories won't diverge too fast. They can only diverge in exponential way. Okay. Okay. So now let's just go to proof the Dubushin estimate, to establish the Dubushin's estimate. But we need a Weissenstein distance. So let me just spend some time give the definition of Weissenstein distance. So now it's more common to call this, but usually people don't call it in this way, but it's called Monch-Kantorovich Weissenstein distance. Usually it's just called Weissenstein distance. And it seems in the computer science community, people usually just call optimal transport or OT distance. Okay. So okay, it's very easy to define. So let's say for any r bigger than 1, so we use PR RD. So we use this notation to represent all the Fourier probability measures. So P is a Fourier probability measure. Right, we only consider Fourier such that the rth moment is finite. So as we did before, that's one P1 and P1. Okay, so this is probability measures with finite moment of order R. So let's say given two probability measure mu and nu, which is in this space, we define a set. So this set is denoted by pi mu nu. So this is called couplings of mu and nu. So what coupling means, right? The coupling means so all the so the coupling means all this probability measure, which is in the space. You can check it's just PR, RD time RD. So such that if you project, so this is a project to the first coordinate, so you get mu. If you project to the second coordinate, you get nu. Okay. Of course, we don't need this R here, but you can check this is the P. Any coupling of mu and nu has finite moment of order R, or finite R moment. Okay, so what this projection really means, right? So the projection pi 1, right? Pi 1 xy is just x. So here x, y are in RD. So so the same, right? Pi 2 xy is just y. Or you can think in the following way. So let's take two test function phi, phi x plus another test function psi y. So then pxy, if you integrate against pxy, so by this property, so this property really means the following. So phi x d mu x RD plus RD psi y d mu y. Okay. So phi psi are test functions. So some we need their growth control as well. But yeah, these are not very crucial. So yeah, just because mu and nu has finite R's moment. Okay, so this is a definition of couplings of mu and nu. So this set, I just want to say several words about this set. It's called couplings of mu and nu. Definitely, this is not empty. I mean, of course, it's not empty. So at least we can take mu cross nu. So when I write mu cross nu, it means tensor product. So basically, it just means that independent, right? If you take two random variable x and y, so x has law mu, y has law nu. If you take the tensor product, it means x and y are independent. Okay, in particular, the tensor product of two measures are their one coupling. So they have other couplings. And you can check this set is a convex set. This set is convex. This set is convex. Okay, excuse me. Okay, so then we can just define a Wasserstein distance. So we can just define Wasserstein distance. I write this as WR. So here R is bigger than 1. So for R bigger than 1 or equal to 1, and two mirrors. Okay, so we define Wasserstein distance as the following. So this is just a minimization over all couplings. Okay, so the most commonly used one are usually the W1, W2. So W1 has a very nice duality formulation, you will see in a minute. So W2, usually they have very nice geometric features. So if you study at least if you study stochastic dynamics, so W2 can be bounded by the L2 distance of two random variables. So W2 distance is also very commonly used. But here we will just use W1. Okay. So if you want to see more details, there's a very well-known book by Cedric Villani. So he has two books, but this one is covers everything. So optimal transport, old and new. But here we will use W1 distance. We will one distance. So we will need a proposition which gives the duality formulation of W1 distance. You can find this in other literature. So in particular, in Villani's book. So I will just write the duality formulation of W1. So what's that, right? Just write a nice, easy way. So original formulation is a minimization problem. So you take the minimization with respect to all couplings. But now we take the supreme over a function space. The function space is just Lipschitz function space. So this means phi is Lipschitz. And we restrict the Lipschitz constant. I write as gradient phi is less than 1. Okay. So then we just compare the integral of this phi against mu minus nu, actually. Okay, this is a duality formulation of one Wasserstein distance. So we will use this to do the Dubochin estimate. I will just do compare two trajectories. So since we can represent both ODE system and mean field dynamics using the same formulation, the mean field characteristics, right? As I write before, is this formulation, right? So we use the same formulation here, right? So we use the same formulation, the mean field characteristic equation, to represent both ODEs and the mean field dynamics. So to compare, so now what we do is just the stability themes. We just compare two flows, just to compare two mean field characteristic flows. Okay. So once we control that, or we get everything, right? It's basically just the stability estimate for continuity equation. Okay. Okay, so again, right, let's just recall, right, in case you forget that. So the mean field dynamics is just this. This is initial data, initial measure. They have two things, right, initial data and initial measure. So for ODE system, initial measure is just the initial empirical measure, right? And we use the formulation we write in the remark before. So here is psi prime. Okay, so we use this formulation. Of course, the initial data is just Kasai, right? Just Kasai initial. Okay. Okay. So now we just compare two characteristic flows. So let's consider two sets. Let's consider this is first two initial data, right? Two initial data, and two initial mirror. So here, so we assume all those mirrors has finite one moment, finite moment of order one. So just to ensure the integral operator, so here is to ensure, so this integral operator is well defined. So Tz z prime f t dz prime. So this is the integral with respect to the mirror f. Since under our same assumption of k, so here, right, so k grows and most linearly. So once we assume initial data has finite one initial mirror has finite one moment, so in this space, so this integral operator is well defined. So this is well defined. So not only it is well defined, but also this is Lipschitz. So kappa f, because k itself is Lipschitz. Since k, the kernel is Lipschitz, the integral operator is Lipschitz. So this is Lipschitz. Okay. So we have this automatically, and this actually is important. So this actually there are two things are very important. So in our case, I will just put here as a side remark. So U in our case, right? The U is the velocity field of the mean field characteristics. So U actually is just a kappa, not a kappa, the capital KF. So T something. So to show, right, actually to get the mean, the distributions estimate, we need two things. So first, this U is Lipschitz with respect to the space variable. So here the dot, and also, right, so U is some, U is KF, right? It's an integral operator involving F. So F is a mirror. So we need some Lipschitz dependence of U with respect to F. There are two things, right? So first, U itself, it should be smooth, right? Lipschitz. Another thing is U is a functional of F, some mirror. So we need the dependence on this mirror is also kind of Lipschitz. I will explain a little bit more after we establish distributions estimate. Okay. Okay, so let's assume we have two mean field characteristics. Okay, we want to compare both of them. We want to compare the distance between them, right, over time. So it's very easy, right? So we just write, I will be a little bit quick, but you can believe them because this is just the first order ODE. So the idea, right, is very simple, right? We just write this in the integral form and take the minus, right? So it's as easy as possible. You can So then we integral over time. So RD, right? So here, right, it's the same things, right? D mu initial psi prime. Then we integrate with time S, right? So this part, right, is something here, but you change T to S, right? So we use this, right? But now we have two equations. So it's psi initial 1, psi initial 2. So mu1 initial, mu2 initial, right? So then we take difference. So we just take difference. So I believe you can recover then. So I'll just write the difference. So it's the following. So Z, so the first trajectory, so minus the second trajectory. Okay. So then there are two parts. So first part is just the difference in the initial data, right? So then the difference here, so kappa k z s psi 1 initial, so mu1 initial, so z s psi 1 prime, so this is integrate 1 initial, so mu1 initial d psi 1 prime. Okay, so then take the minus ds, so k zs initial mu2 initial, so zs 2 prime 2 initial, so mu2 initial. Okay. So another observation I want to say, okay, so we need, so here, right, so basically we take, so we just take the difference of these two terms, but they are integrate with respect to different mirrors. But if we choose, right, so now we choose any mirror pi initial. So this pi initial is a coupling of mu1 initial and mu2 initial. Okay, so if we choose pi initial, and we can represent these two integral, right? The difference of these two integral as the integral of the difference. Right? So I will just write, so these two terms here, equals, right? So equals. So this is, again, we use the change of mirror formula. So here is K. It's just A. So this is A. This is B, right? It's just A minus B. But here the integral is the following. So it's D pi initial. So psi 1 prime. So let's write it in another way. But these two are both, these two formula are both used. You can choose which one you use, but this one. So originally it integrated with mu1 initial and mu2 initial, right? But now we use their coupling. So we can write the original the difference of two integrals as now the integral of difference. So this is just a change of mirror using change of mirror. Okay. So now we get the nice form. So I will write everything we get. So now So maybe I just put a one note here. So here they say we have f cosine 1 d pi 1 prime, right? Uh, so they're both used, but let me just use this, right? So this is RD cross RD, right? Since the push forward, right? We took the projection map, right? The push forward. So so pi 1 push forward, pi initial. The pi 1 is a projection. So which is just mu 1 initial. So so by a change of measure formula, so what we get here is just this. So what we use is just this equation twice. Okay. So if we sum up, right? If we sum up what we get, so we have the following. So z. Yeah, if you have questions, you can ask me. Okay. Minus z t initial mu2 initial, so one initial, sorry, 2 initial, so plus this. Okay, so k z s initial, so okay, so that's what we get. Okay. Okay, so now we just using the we use the Lipschitz property. We use the Lipschitz property of k. So k is Lipschitz both in the first variable and the second variable. So in particular, we use this. So let's say we have a prime, and we take the difference of k b prime. So we just get l a minus a prime plus b minus b prime, right? So it's a very easy observation, just using one just using like just using the Lipschitz property of k, right? Plug one term and you can get that. Okay, is that maybe I should change a little bit, right? So it's my fault. So a minus b, a prime minus b prime. Okay, so now what do we have, right? So we take the difference. So we take the difference. So the absolute value so t cosine 1 2, so mu2 initial. So this is less than the initial, the first term, right? Just a trivial estimate. So L. So we take the difference of this term, and there's a L here, and also this term, and we give the second term, right? There's L factor there. So you can check this by yourself. Okay. So because here, right, the difference of these two terms, right, the difference of these two terms, there's no variables like Kasai 1 prime, Kasai 2 prime. There's no integral. There's no the inner integral here, right? So we just get a constant. Right? But for the second term, we have the second integral. So which is S. So ds. Okay. So we are almost done. So as long as we introduce one notion here. So let's call, introduce one notion here. So let's call this notion d pi initial, right? So this, the mirror is here. This is with time s. It's with time s. Okay. So let's introduce this notation, and so I just said that and we integrate with respect to this variable, 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 with respect to pi initial again. Okay, so we integrate both sides with respect to the measure pi initial. So pi initial is any coupling we choose. So which is any coupling we choose of mu1 initial and mu2 initial. Okay. So we integrating both sides with respect to. But now the variable change, right? It's not originally Kasai 1 prime, Kasai 2 prime. So now is we integrate the variable. So now the variable is Kasai 1 initial and Kasai 2 initial. So then we will get, so gives the following. So this term doesn't change. So the last term doesn't change, right? It's just L times this, but this term change, right? We integrate with respect to here, this variable, Kasai 1 initial, Kasai 2 initial, right? So we end with this d pi initial again. So there are two terms. So now there are two terms. Okay, and they are integrated with time. So this is what we get. And this term, so what is this term, right? What's this term? This term is just initial, it's just a d pi initial, d pi 0. So we get integral inequality. We get a differential integral type inequality, right? We can apply an integral type Grunwald estimate. So by Grunwald again, I mean, if you're not familiar with Grunwald, you can find this almost everywhere. So by Grunwald, integral type Grunwald inequality, so we can estimate this. So we can get so this directly. We can estimate this directly. This almost is distribution estimate, but we need to use this information. We want to use this information, d pi initial, to recover W1 distance. And W1 distance will matrize the weak convergence of measures. Okay. So one word about Grunwald inequality. Right? Basically, you can just let this to be equal and solve the upper bound. And if you solve this integral equation, which can be solved by solving a differential equation, and if you solve that, this the solution gives you the upper bound. So basically, it just solve ODE. Okay. So now we are almost done, but we need one step to recover W1 distance, the one Wasserstein distance from the quantity we define here. So the quantity we define here actually is almost there. Right, you see, so this is the quantity we define, and this quantity defined actually is kind of a control of one Wasserstein distance. So I will just continue. Okay. Recover. So how to do that, right? How to do that? Okay. So recall. So we have two characteristic flow. We have two characteristic flow, mean field characteristic flow. So which push forward our initial mirror to the mirror and time t. So since we have two choices, right? We have two choices. So G here equals to 1 or 2. So we have two choices, right? This is mu1 initial, right? And cosine 2 initial and mu2 initial. Okay. This gives us the t, the first characteristic, and this gives us the second characteristic. And what we are doing now is just compare these two flows. Okay. So if we compose, if we just compose a big map by putting these two flows together. So we have one map, one bigger map. So this is initial since. So if cosine 1 is initial, cosine 2 is initial, right? So what this phi t do? So phi t just send them to cosine 1, sorry, t initial data, right? I think I can, yeah, but it doesn't matter. I don't need to put a real initial there. So mu1 initial, z t cosine mu2 initial. So this is the joint map. Okay, and you can check easily. So this map push forward pi initial. So pi initial is a coupling of mu1 initial and mu2 initial. So if you take the push forward map, you get a mirror, right, which depends on t, the parameter t, the time. So mu1 t, mu2 t, and you can check this very easily, right? Just using the composition of two maps. So you can check pi t is one coupling of mu1t and mu2t. It's very easy to check. It is just a composition of two maps. Okay, so since pi initial is okay, so we can write the Weierstrass distance using the duality formula. So if we want to control W1 distance between mu1t and mu2t, so we're using the duality so it's not the duality formulation. Okay, so here we didn't use the duality formulation, but we use the duality formulation. We kind of, sorry. So it's not, we not really use the duality formulation. So we use the duality formulation later when we say Weierstrass W1 distance matrix reconvergence. But the proof we have done up to now actually is just the duality formulation of one Weierstrass distance. It's just put in another nice way. So yeah, but here, right, in this particular argument done by Gauss in his notes, we kind of didn't use the duality formulation explicitly, but we used that before, not in an explicit way. Okay. So we just using the original formulation. So pi. Okay, so this is just the definition of one Weierstrass distance. So if we restrict the Inferman domain, so it becomes bigger. So we can just restrict all this pi. We restrict all this pi to the push forward of pi initial. So and we change our measure, so we can. So it becomes bigger, right? Possibly they are equal, but at least you put this sign here is 2. So Z T Z T. Okay. And this one is just the Inferman of pi initial, mu1 initial, mu2 initial. This quantity is just what we define, and d pi and time t. And we can use the previous estimate, right? The previous estimate involving d pi initial is true for any coupling of initial measures. So we can control this. We can control this. And so if you look at this formula, right, it's exactly the definition of one Weierstrass distance. So because now you're taking against, the minimum is against all possible couplings with, of the initial measures, right? So we take the minimum with respect, we run the minimization over all possible couplings. So so this term, right, last term is just a one Weierstrass distance. Okay. So if we just sum up everything, right, this is the one Weierstrass distance and time t. And this is one Weierstrass distance and time 0, right, initial. So we obtain Dubushin's estimate. So which is just W1, so mu1t under all our assumptions under above. On all our assumption above, we have the following. Okay, so we are done. And so the mean field limit part is just the corollary. And you can, so you are, so I just say a few words, so now okay. So now if we choose, so what is mean field limit? So let's choose, so mu1t, mu2t are all solutions to the mean field dynamics. So here, mu1t, mu2t are two solutions to mean field dynamics with initial mirror, initial data, mu1 initial, mu2 initial, respectively. So, so if we choose, right, so if we just choose mu1t as our target mirror, we want to approximate by particles, right? So this is our target distribution. So you can assume it's a density function, or it can be not. So, and mu2t, let's assume mu2t is the empirical measure, so which is just this. Okay, so initially, right, so if initially, right, this goes to 0, so Dubushin estimate gives us, so W1 F T, so let's write it, T, and here is mu and T is empirical measure, 2LT W1 F0 and mu n 0. So mean field limit basically says if initially this sequence, right, it's a sequence of empirical measures. So if this sequence of empirical measures converge to F0 as n goes to infinity. So by Dubushin's estimate, right, the distance between the t time t empirical measure and the time t PD solutions are also very close. So which means if you send n goes to infinity, the distance measured by one Wasserstein distance goes to 0. So this is a mean field limit, and this is a very classical result, I think due to many people, not just Dubushin, but this is the starting point for many works, maybe in last 10 years, involving Lipschitz, non-local Lipschitz interaction kernels. So there are many works involving using Dubushin estimate. I don't have time to talk about that, but you can read more discussion in the Ghost notes. But next time, I won't use Ghost notes again. But these are classical work, and it gives you explicit convergence rate. So I call it quantitative methods. So if you want to know more about for kernel K, which is local Lipschitz, and for all kind of related models, like swarming model, flocking model, and in neuroscience or machine learning, so there are probably many literatures. I just want to so point one, so which is a review paper by so just let me show you. Okay, so it's just this paper. This is a not very old paper, and you can so here summarize many works using Dubushin's type argument to derive kinetic equations or aggregation type equations. So by Carrillo, Choi, and O'Haye, and they have many recent results as well. Some of you might be interested. So the review paper by so in particular, right? So they can control W infinity distance or between empirical measure and the limit for some aggregation type equation. So for this type of equation, right, for here k equals to minus w, right? And so of course, right, the target, the expected limit reads like this as well, right? So they can control, right? For instance, so W, I think alpha is less than D. Yeah, D minus 1. So they can do this up to Coulomb, up to Newtonian potentials. So those are 7 years old paper. So recently, for deterministic systems, Sabaty can cover the Newtonian case. So I won't talk about other extensions of Dubushin's estimate. There are many papers extending classical works like by Dubushin and others. Okay, so from next week, I will talk about my works using relative entropy. So basically, there are several papers, but next week I will cover so the relative entropy method. So we will consider stochastic system and also deterministic system. So the setting looks different. So here, the convergence, the empirical measure can be just deterministic, right? So mu n here can be just a deterministic measure, right? It's just a measure. But usually for stochastic setting, like here, if you put a noise, so the empirical measure becomes stochastic, right? It's a random empirical measure. And there are some works, right? The classical work is very old, like date back to, I guess, at least 1960s, McCain. So in stochastic setting, the very famous method called coupling method, if you assume K is Lipschitz and bounded, so basically the argument looks very familiar with the previous calculation I did today, like what we did here, like what we did here. So you basically compare two trajectories. One trajectory is just the ODE or SD system. So another trajectory is symmetric, I call it symmetric systems. It's just n copies of the limit system. And you compare both of them, and you can control the growth of their distance by Gromov estimate. So next week, I will spend a little bit of time talking about stochastic systems using coupling method. So then I will go to the relative entropy method. Yeah, and so next week is like relative entropy method and type 1. I call type 1 large deviation estimate. So then if we have time, we will go to the second type estimate, large deviation estimate, and introduce the new method we just introduced last year. Okay. Yeah, I will stop here. If you have questions, you can ask. Oh, okay. Another thing. I post everything, my notes and recording on my YouTube channel. So, but I'm not sure people from China can access YouTube. So I also put my notes there. So you can find the notes under the description. Okay. I will contact the staff in Tsinghua University to upload my recording, maybe in Bilibili something. Yeah. Okay. Yeah, if you have questions, you can ask. Okay. Okay. No questions. Thank you. Okay.